Hello everyone, my name is Nico Bollinger and today I'm going to talk about learning multi-embodiment locomotion. This talk will be mainly centered around the CORL 2024 paper One Policy to Run Them All. But before we dive deep into the nitty-gritty details of this work, I want to take a step back and look at the current state of the art in robot locomotion. And what you're seeing here on the screen are three works that came out early 2023, essentially back to back to back, showing really good agile quadruped parkour locomotion. And this is more or less what we currently can do, at least with the quadruped form factor. And how does this essentially work? The field in robot locomotion more or less converged to the Lego Gym codebase published by Nikita Rudin in 2022, meaning he was the first person to put everything into one open source codebase with all the things that you need to actually learn these policies and to deploy them on real robots. Now, what is in there? It is essentially built on top of Isaac Gym, meaning GPU simulation with thousands of parallel environments to collect a lot of data points and a lot of rollouts to train PPO with big batches. Now, these policies are usually command velocity conditioned. This means they get an X, a Y, and a yaw velocity as an input in the trunk frame, which the policy needs to learn to follow. And these policies can then be controlled after training with a high-level policy or with a human operator that uses a joystick. Now, a bit of an implementation detail, but still really important, are how the actions are managed on these systems, because usually the policies produce target joint positions, which are tracked by a PD controller at 50 Hz. And the actions are used as follows. They are scaled by some scaling factor and then added to a nominal joint position, which is usually a good standing position of the robot. This is really important at the start of training because usually the actions are centered around 0, and now we're centering them around a good standing position, which makes exploration and learning really nice and efficient at the start of training. Now, because we are doing RL, we need the ominous 10 billion reward terms, which in locomotion are usually 1 to 2 terms for tracking the velocity command, and then a lot of terms to shape the gate, use less energy, and just make sure that whatever we learn is hopefully more applicable to for sim to real transfer. And then I guess the most important part is doing domain randomization on essentially everything. So looking at the simulator, all kinds of attributes like friction or masses of the robot, or even the PD gains and the strengths of the motors. Whatever you can get your hand on should be randomized. And to an extent that is quite extreme, things that are might not even realistic, that we would probably never encounter in the real world, still, because we don't know all the axes that we should randomize on, and we only have a certain set, we try to randomize them as much as possible to be really robust and general to whatever we might encounter in the real world and to whatever sim to real gap we might have. And then finally, to train really impressive parkour policies, as you've seen them on the last slide, we use student-teacher training. This means we are training a teacher policy that also takes in privileged information that we only have in sim. And for visual policies, those are also things like height samples around the robot. And then we train this teacher for a really long time and distill what it learned into a student policy with Dagger, where the student only gets observations that we have on the real robot. And for visual policies, that also means then depth images. Now, this is the pipeline that the field currently developed and is using essentially all the time. But what is missing? What is still interesting research to be done? One thing is, for example, visual navigation policies, so really training them end to end, or using already existing robotics stacks to integrate the learned policies. These things are already done currently, but there's still a lot of work to do in my opinion. And then I guess the most important one is combining locomotion with manipulation, or short local manipulation, as just walking around in the real world is not really solving that many interesting tasks. Combining it with manipulation, though, opens up a wide range of really interesting tasks in our real world. Now, besides that, we also see the advancements in building robots, and with that, more and more robot platforms coming out from different companies, and especially also falling in prices to an extent where nowadays every robotics lab has at least a quadruped, and probably already has or soon will have one or more humanoids. And this is thanks to advancements in the field, but also companies like Unitree really pushing the prices and making these robots really affordable. Now, with that in mind, our current paradigm of training a neural network policy for one robot can be kind of annoying, especially if we are a lab that gets new robots or more and more robots over time, or all the time even, and now we need to train new policy for every robot. And besides that being just cumbersome, we also know from other fields of machine learning that if we could train a general single network that can control all of them, this network might be a lot more powerful because it could reason about or across all of these different robot platforms at once and might understand the task, in our case locomotion, on a deeper level. So we want to learn, or we want to be able to train a policy like this. But how do we do that? There's already prior work on morphology aware or morphology agnostic policies. And in the age of deep learning, this mostly started with graph neural network based methods, where essentially you can view a robot with different amounts or different body parts or different joints as a graph, where essentially each body part or each joint now represents a node. And we use graph neural networks to give every of these nodes observations, and then use local message passing to accumulate all the information and then produce actions for every node as well. Now, as everyone probably knows that used the GNN before, these things are sort of hard to train, and also especially the local message parsing is often quite a bottleneck to get really powerful policies. Therefore, the field moved on to transformer-based methods that were still really inspired by GNNs, but now we had a lot more powerful policies, or a lot more powerful networks with a lot more parameters, though we still needed to use handcrafted joint tokens per morphology that we predefined, so this was still not really that general in a sense. And also all of these methods, GNNs and transformer-based ones, were only ever applied to 2D planar robots walking into one direction, which meant for me that I wasn't really sure if these things really scale to arbitrary robots, even in sim, that are more realistic than these simple 2D planar walker type systems. Now, what gave me a bit of hope was in end of 2023, there was this many quadrupeds work that took 16 different quadrupeds and even real ones in sim and learned one policy and then even deployed this policy on some of the quadrupeds. Now they were using a CPG with inverse kinematics, so essentially predicting the next foot positions and then tracking this with IK. But for their system, they just threw away all the joint-specific observations because they didn't know how to deal with the different amounts of observations they now had. And this only works if you have the same amount of feet for all of your robots, else you would need to learn a new CPG again. Now, the question that I wanted to ask was, or is, can we learn a single general locomotion policy for any legged robot embodiment or morphology? Really meaning a single policy that can generalize and reason about all kinds or multiple robot embodiments. And doing this with reinforcement learning from scratch, So you could also go into the direction of imitation learning, but I really wanted to do RL here from scratch and training on many realistic simulated robots, so no 2D hoppers anymore from different morphologies, and then evaluate hopefully zero-shot transfer on unseen real robots. Okay, with this goal in mind, does this even make sense? Is this even feasible? Because one might ask if the pipeline that we developed for all of these really impressive quadrupeds might be totally overfit to this platform. Because there are so many moving parts in there, the reward terms themselves, the coefficients, the control schemes, the gains, the domain randomizations, all kinds of things in there are heavily tuned probably to the platforms that we've used them before, which are mainly only quadrupeds. So I asked myself this question, and when last year Unitree came out with their Unitree H1, their first humanoid robot, I thought that why not just try this? Why not just take the URDF that they published and just throw it into the simulator or throw it into the code base that was developed for quadrupeds, load the reinforcement learning training and just look at the initial policy and eyeballing the p gain and and the torque norm penalty, because I saw that the robot needs a bit more power to actually stand up, but produces more torque. So just eyeballing like two values and then running the training overnight and seeing what happens. And the result of this first training run is what you currently see here on the screen. So this robot actually learned to walk quite well. Now, besides the really funny hand and arm movements that it's doing, it's actually really robust and can walk in all directions and turn, and that even at really high speeds as well. So this result gave me the confidence that this is actually feasible. The pipeline that we built for quadrupeds is so good and so robust that we can just throw in another type of robot, a completely different type of humanoid, eyeball two values, and it already works out of the box. Now, with this in mind, how do we get to now an actual policy that can walk with all kinds of robots? Because the core problem of multi-embodiment learning is, at least in our case here, is we now have different observation and action spaces. And if we look at the observations, for example, we have some general observations which are of fixed length and always the case for all of these robots that we might care about, which is, for example, the angular velocities of the trunk, which is the command velocities that we're giving to the system, and all of these things that are fixed with or are of fixed length. Now, most of the observations, though, are robot specific. For example, joint specific observations, they scale with the number of joints of the robot, and feet specific observations depend on how many feet we have. And the same for the actions as well. As we are producing target joint positions, we need to produce them for every joint that we have, and this can now vary in the amount of joints, right? And as you all know, we have neural networks. They can only really take in fixed length things and produce fixed length things. So we somehow need to think about how we get all of these observations into one vector and produce one vector again. And I thought about this as a sort of routing problem, where essentially we have, for example, observations here from a certain quadruped. Quadruped 1 has observations for its front right hip. And this observation should maybe be placed somewhere in this big fixed length latent thing. And if we have another quadruped with its own observation, but also for the front right hip, this should probably be at the same place. But if we now have a humanoid with some shoulder observation, this might be somewhere else in the latent. And if we have the knee observation of a leg from a hexapod, this should probably also be somewhere else. So now what we are doing is we take observations and we put them somewhere in this latent vector based on their description, which I just explained with words, the description being the left shoulder yaw of this humanoid. Now we somehow need to map observations and descriptions to values that we can actually use with a neural network architecture. And for that, we can look at, again, for example, a front right hip of, now in this case, a Unitree A1 quadruped robot. And the description vectors are now, or the descriptions are now not just language descriptions that are kind of loose. They are attributes of this joint. So for example, in a nominal position, where is this joint located, right? What is the rotation axis of this joint? Like, how does the joint rotate? How many child joints are following after this joint? So where is it in a certain kinematic chain? What is the nominal position of the joint? And then what are other attributes of like the motor, right? What are the torque limits, the velocity limits? How far can the joint move in min and max range? And all kinds of other attributes that can help us to describe a certain joint and help us to differentiate between joints. And on the other hand, the observations are rather simple, so we use the classic observations that are used for joints, so the position of the joint, current velocity of it, and the previous action, right? So now we're splitting joints into dynamic observations that essentially change on every time step, and description vectors that are fixed and help us to describe different joints. Now, we need to encode them into, which I showed you, into some fixed length latent thing. And we do this with an attention encoder, or something that, looks like the attention scheme that you might already know. So here we have on the left side the joint observations and the joint descriptions again. And now in a world of attention, you can think of the descriptions as the keys of the attention scheme and the observations as the values. And what we do in attention, we take the keys, in our case these descriptions, we encode them, and then put them through softmax. And if the softmax, or if the system is already learned, then hopefully the softmax for a given joint will only be close to 1 for like one index, and everything else might be close to 0. Let's suppose it's already this way. We then can also encode the observation of the joint and multiply it with the result of the softmax. And this will lead to the observation only being present where the softmax was close to 1, because this observation is then multiplied by essentially 1. And everywhere else in this vector, it will essentially be 0, because the observation times 0 will be 0 again. And this will produce the latent encoding for this joint. And now what we can do, we can batch or encode all of the joints that we have in a batch in parallel, and then we can sum them up. So with all the joints encoded, no matter how many we have, we encode all of them, sum them up, and now produce a single joint latent vector. And if the system was learned, the network can put certain information of certain joints in different parts of this vector. And the sum helps us to get rid of the problem that we have varying amounts of joints per robot. Now, with this latent vector produced, we take it for the joints. We also do the same for the feeds as well, because we can have different amounts of feeds and we have feed observations. We take these two latents and concatenate them with general observations that are, as I told you earlier, always of a fixed length. Encode all of them in a big core network. So here are the biggest layers of our neural network, where it can learn to reason about all of the information that it has. And this produces a last latent, which we call the action latent vector. And now to actually produce the actions of all the joints that we have, we take this action latent vector and concatenate it with a joint latent and a joint description of a given joint, and then produce a single value, or in case of PPO, where we have a mean and standard deviation, those are two values, which are now the action for this given joint. And then again, we can do all of this in batch and just produce as many actions as we have joints. and then execute this on the given robot system that we currently train on. Now, this architecture we called Unified Robot Morphology Architecture, URMA, in our paper. And with this in place, we did also some theoretical analysis. And I don't want to go too much into detail and want to bore you with too much theory. But essentially what we do is we frame the PPO learning as a sort of regression problem for 3 different components, them being the encoder, the core network, and the decoder. And we take some risk bounds from the literature, from the multitask reinforcement learning literature to be precise, for multi-head architectures. And we show that our URMA architecture scales inverse proportionally with the amounts of task, which makes inherently sense because the more robots, which are tasks in our case, we're adding to the system, or that we already have, the easier it is to learn a new one. Whereas for a multi-head architecture, we always need to learn a new head, decoder and encoder for every new task, or in our case, for every new robot that we add. With that in place, let's look at some of the results that we have in simulation. And what I'm playing here to you are the 16 different robots that we have in sim and that we train on. So we have 9 quadrupeds, 6 humanoid robots or bipeds, and 1 hexapod. All of them trained in MuJoCo on the CPU actually. And yeah, with 3 environments per robot, we have 48 parallel environments training for 100 million steps per robot, which makes 1.6 billion steps in total. And what you see here is the MuJoCo simulation after training. And actually on the left, on the top left, you see a QR code to our project page where you can try out these robots in MuJoCo in your browser as well. So give that a try. Now, to some of the results, we compare our training of our URMA policy, which you see here in blue, with 2 baselines, which are a multi-head baseline and a padding baseline, where in the padding baseline we essentially take in all of the observations and 0 pad whatever is not present for a given robot. And then we compare it to single robot training. And most importantly, here in the dashed line, you see the single robot training case where we take the 1.6 billion steps for a single robot, which is essentially the best that you can do. So this is essentially our oracle of performance, the best performance that we can achieve if we train for a really, really long time for every single robot. And our system that only takes in 100 million steps per robot is already quite close to that performance. And if you would train this longer, you probably even converge to that in the end. So we can take in only a 16th of the samples and still train a policy that can work with all of these different robots as you've seen in the previous video, which is really nice. But we wanted to mainly also investigate the zero shot and fine-tuning performance of this policy. And we do this here in 2 experiments with quadrupeds, on the left with the Unitary A1 and on the right with the MAB Silver Badger. And for the A1, that's quite straightforward. So what we do is we only train with 15 robots from our training set and essentially leave out this A1 quadruped, and then always in the background of training, 0 shot evaluate on this robot. And we see here in blue our performance really quickly converges to the perfect single robot training case. So essentially we can totally 0 shot transfer to this robot. Now, in the case of the MAB Silver Badger, this quadruped is a bit more special because it's the only quadruped in the training set with a spine joint in the later part of the trunk. So we don't have any other quadruped with this type of joint, but at least we have some humanoids that also have more or less a spine joint or a joint in their back. And still the rest of the quadruped form factor should apply to this robot. And we see also here, if we evaluate 0 shot performance during training, we improve and get reasonable, walking behaviors at the end. But now what we do after 100 million steps, 1.5 billion for all of the other robots, we do 20 million steps of fine-tuning only on this quadruped, and then you see that we spike up in performance and get really, really good performance. So with pre-training on 15 other robots, we still get reasonable zero-shot performance, but then with a bit of fine-tuning, we can actually get really robust behavior. Now, our method is obviously not magic, and this is what you can see when trying to zero-shot on humanoid robots. As we only have 6 different humanoids, if we now leave one out and only train on 5, these humanoids are still quite different to each other. And we're also not doing the biggest ranges of domain randomization in this work for the humanoids because we did not plan to transfer to real humanoids here yet, which hurt the generalizability for the humanoid form factor. So what we try here is the same thing. We train our URMA policy on 15 robots, what you see here in green, and leave out this unitary H1 humanoid. And if you do zero-shot transfer or evaluation during training, you see that you essentially have no performance on this robot. Because the humanoid form factor is so unstable also, if you don't know what you're doing with the robot, you will essentially fall immediately and don't get any performance. But now we are doing the same thing as with the previous quadruped, where after the training is done, we take 20 million steps only with this H1 humanoid and fine-tune, which you see here in blue. And then we spike up in performance immediately and get really good locomotion behavior. And this is even faster than just training with this robot from scratch or having it part of the training set. So what you see is that that our architecture actually learns about the humanoid morphology, and if you then give it a bit of time to fine-tune, it can quickly adapt to a new robot, which is really nice. But as I said, it's still not magic, so zero-shot performance is currently not happening here. Now we also wanted to test a bit of robustness, and we plan to do a lot more robustness tests in the future because we now have this additional axes of randomization, which are the robot embodiments. And we tested this already a bit in this work where we checked for the robustness to observation dropout. And what you see here is our policy in blue and the baselines in green and red again. And we are dropping out the foot observations. So the policy being usually trained with foot observations and now evaluated in the background with dropping them out. And our policy is really robust to that and can still walk without an issue, even when the foot observations are dropped out, which is already a nice sign for robustness. And another thing, or the last thing that I want to show you from the results from SIM, which I found was quite neat, is how the policy actually conditions on the different attributes in the description vectors of the joints. So what I was testing here was taking 3 different parts of these joint descriptions, first being the PD gains and the action scaling factor, the joint rotor inertias and the joint friction coefficients. And then what we're plotting here on the y-axis is the average action norm. So essentially how big is the action, how big is the magnitude of the actions in on average. And then what we're doing is we're varying the scale of these attributes. So usually they are at here factor 1, which is their usual values. And then what we do is we multiply them by 3 or divide them by 3. So this means here in the first case, we essentially give to the policy PD gains and action scaling factor and description vectors that are 3 times higher, or only a third of their usual values. And what we see now is that the policy actually responds to that. So if we have a motor or a joint that acts more aggressively, so uses higher scaling factor and has stronger PD gains, the policy tries to counterbalance that and therefore produces actions that are lower, such that we don't overshoot. And it does the opposite if these things are smaller, so essentially the PD law reacting not as strongly, then it tries to overproduce the actions, so produce higher actions to counterbalance the lower gains. And we also see this for the rotor inertia and the friction coefficient. Now, if we increase the inertia or the friction, this means the system reacts less on the actions that we are given, then the policy produces higher actions to counterbalance that. And if we decrease the inertia on the friction, so the joints are more responsive, also the policy will now produce actions with a lower magnitude to not overshoot again. So the policy really learns to reason about the attributes in these joint description vectors, which I found was really cool. Now, for the real-world experiments, we take our URMA policy and deploy that on 2 quadrupeds that we already know from simulation, which is here the first one, the Unity A1. So this was part of the training set. And due to the strong domain randomization that we do, we can easily transfer to this robot. And even though we actually only train on perfect flat ground in sim, we can still walk on different kinds of terrain. And we do this with a second quadruped as well, which is again this MIB silver badger with a spine joint. And also here we can perfectly well zero-shot transfer on this robot, as we've already seen it from sim. And the training pipeline is really adapted to make the sim-to-real transfer happen. Exactly, and we can walk about over different bumpy grass terrain and even with a bit of inclinations, which is not a problem as this policy is really robust. Exactly. And what we then do is we try to transfer zero shot to an unseen quadruped that was not part of the simulation training set, which is this honey badger robot. It looks quite similar to the silver badger, but as you see, it doesn't have the spine joint and therefore is a lot shorter and also a lot lighter. And we've never seen this in training, but still we can perfectly zero shot transfer to the real version of this robot. And also walk over different types of pavement and bit of bumpy grass terrain without any issues. So the only thing that we need to know is the descriptions of these joints, and then we can run the policy essentially out of the box. Now, the gates are not really perfect yet. Especially if you walk on some slope, because as I said, we've only trained on perfectly flat ground. So if you also had more challenging grounds in the terrain, you would probably get a bit nicer in simulation. You would probably get a bit nicer gates. But still, these policies are really robust and have no issue walking over all kinds of real-world bumpy terrain. Now, for future work, there are essentially 2 directions that I'm currently interested in. The first one is actually deploy the URMA policy also on humanoid robots, as we've now got a Unity H1, which you just see in this video here. And we will soon get even more humanoids. So that will be really exciting, trying that also out on a different morphology. And then I want to move to more challenging terrain, uneven terrain, stairs, obstacles, and parkour stuff that you've seen or that I've shown you in the start of the talk. And for that, using exteroceptive information and trying to encode them in a clever way. Because robots can have depth cameras, they can have lidars or multiple cameras or multiple lidars or some combination of these things. And again, we don't want to retrain or train a new policy every time we have a new type of exteroceptive observation or a new combination of cameras. So we want to come up with a clever encoding scheme also for these types of observations. And then things like history encoding just fit really naturally in our architecture, as we can just add another dimension to these description vectors, that being how old an observation is, and now we can use history of observations without any problem as well. And a second interesting direction would be to really hone into this zero-shot transfer capability of the policy, and do that with procedurally generated embodiments and train on thousands of them in parallel. So we generate blueprint robots essentially all the time, constantly doing training, and then maybe even based on policy performance, generate different embodiments again. So maybe we figure out halfway through training that we are already quite good with quadrupeds, and then we will produce more humanoids and so on. So we can only train on like these really different embodiments, and then hopefully zero-shot transfer to real robots. And there's already kind of interesting work that thinks about how you can generate procedurally different robots. So integrating this into the training pipeline and then coming up with a really general robot that is trained on all kinds of different morphologies and embodiments would be also really cool, I think. And in general, where I want to move this work to is towards generalist policies. And I think this, in my opinion, generalist policies have to be embodiment aware. So no matter how you do it, I think these policies should be able to reason about the embodiment they're in and act accordingly. So for example, you can think about an agent that takes in the robot's URDF or even the manual of the robot as an input, as maybe an additional context, and then produces actions that are actually embodiment aware to solve any kind of task. So this is essentially the vision that I want to move to with this work. And that's it.